Hello everyone, this is part 2 of week 10. This is where we're going to talk a little bit more about regression, especially multiple regression. To start, let's talk about our example of simple regression that we talked about, chocolate consumption and car accidents. Let's say this is the data that we got from a bunch of different states, and it looks like chocolate consumption might cause car accidents. There's a strong relationship there. The question is this accurate? Or in other words, what else could be explaining the relationship between these two variables? Is chocolate consumption actually causing car accidents? Well, what if we control for the time of year? When we control for the time of year, let's say this is what happens. It's likely to be the case when we take out the part of the relationship between chocolate consumption and car accidents that's related to the time of year. This is what we're left with. There's no relationship. As chocolate consumption increases, car accidents don't increase. It's just flat. So I used two terms there. I used control for, and I said take out. In essence, when we include another variable in the model, what happens is that the part of the relationship between the two variables that we were looking at before that's related to this third variable that we put in, that third variable is being controlled for, or we're taking out that part of the relationship, the part that's actually related to this other variable. So let's look at this example and how it would look from Jamovi. So the two models, we would have the simple relationship where we're looking at chocolate consumption predicting car accidents. And let's say this is the result. We get this model out and we don't really generally interpret the intercept. It's just part of the model to make it correct. So we can ignore that line. So we look at chocolate consumption, and the estimate is 0.64. So what that means is for a 1 unit increase in chocolate consumption, car accidents increase by 0.64. In this example case, those units may not be super relevant, but the idea is that as chocolate consumption increases, so do car accidents. And if we look, this is significant. In other words, there's evidence that these two are related and maybe chocolate consumption is causing more accidents. But if we control for the time of year, we're going to see a different story. Suddenly, the chocolate consumption, the estimate on it, is much smaller. It used to be 0.64, now it's 0.18. And if we look, it's no longer significant. Rather, the time of year becomes significant, and its estimate is pretty high. So what we have here is, when we just looked at the simple relationship between chocolate consumption and car accidents, it looked like there was a relationship. And it could be that chocolate was causing car accidents. Maybe it was getting people drunk. They were feeling so good from chocolate that they would crash. So that was what this box is highlighting right here. That's that relationship, the simple relationship. But when we actually control for time of year, what ends up happening is chocolate consumption, the part that was making it look like it was related to car accidents actually gets pulled out because it actually belongs to the time of year instead. What happens is chocolate consumption is no longer significant, and time of year is actually what explains it. In other words, chocolate consumption doesn't predict car accidents. It's only the time of year, and chocolate consumption happens to also be related to time of year. Hopefully this is helping you understand what this means when we say controlling for. We're taking that out of that relationship between chocolate consumption and car accidents. We're accounting for it. We're holding time of year constant, those are all meaning the same thing. You'll see them all in the literature. What they're trying to say is that we're accounting for it. So that the relationship, when we account for time of year between chocolate consumption and car accidents, isn't due to time of year anymore. We know that this relationship, even though it's not significant, this 0.185, is not related to time of year. Could be related to something else, or maybe there is a really small relationship between chocolate consumption and car accidents, but it's not due to the time of year. As a reminder, the first model was a simple regression. It only had one predictor. It only has chocolate consumption. The second model has more than one. It has two in this case. And so it is actually a multiple regression. Another thing to note is in both of these cases we have an R-squared value, in this case 0.389. In other words, we have a large effect size happening here. Chocolate consumption explains almost 39% of the variability in car accidents. That means by just knowing chocolate consumption, we would be able to guess what the car accidents number is pretty well. But when we include time of year, it increases even more to 0.56, which means the two variables here, chocolate consumption and time of year together, explain 56% of the variability in car accidents. Together, these two pieces of information tell us a lot about car accidents. However, if we just had time of year on its own, it would probably explain the majority of this. What that means is much of this effect right here is actually just due to time of year. This means a few things. For one, we want to control for things that should be controlled for. We want to account for anything that could be confounding the relationship between our predictor and the outcome. Because it might look like it's really important, a really big effect size, but it turns out most of it is just due to time of year. Now that we have more than one predictor in the same model, this changes the interpretation just a little. Now the slope means the change in y for a 1 unit change in x while holding the other predictors constant, or controlling for the other predictors, or accounting for the other predictors. That all means the same thing. It also changes what we are estimating. Instead of finding a single line, technically we're finding a plane, like a flat plate. We're trying to find the best fitting plane. We're not going to go into a lot of detail on that in this class. If you go on to further regression, we'll be able to talk about this more. What it's trying to do is still find the best fitting slopes that tell us the most about the data. If we go back to our example here, these are just slopes. This is the slope for chocolate consumption. When we include time of year, this is the slope for chocolate consumption, and this is the slope for time of year. In other words, for a 1 unit increase in any of these, this is what we think car accidents will change. So if I increase time of year by 1 unit, car accidents will increase by 3.2 units. As you can guess, when we do multiple regression, it introduces a few complexities, a few things to think about. The first is variable selection. How do we decide what to actually include in the model? Well, generally, what we're going to do is we're going to include the variables that theory would tell us are related, that we should control for. Sometimes it's going to be based off of researcher intuition. We think this is what we should include in the model. Sometimes it's going to be based on checking correlations between different variables and seeing what are related to each other. Variable selection overall is really important and is a place that we often need to spend a lot of time thinking about when we're doing a regression model. Next thing we need to consider is assumption checks. We're going to talk about this one in just a moment. But it actually, even though it seems like it could get more complicated, overall it doesn't get overly complicated, that we can still check assumptions. Third, multi-collinearity is essentially the fact that two predictors can have so much overlap that the regression can start to get confused over which one's which. They can have so much overlap that there's not a whole lot of information that's unique in one and the other, and that can cause problems in the regression. We'll talk about that more in a sec. And then interactions. Just like in ANOVA, we can have interactions here. Variable selection when theory is unclear, there's several approaches. The first is forward or backward selection. The book talks about this a little bit. There's a machine learning approach called lasso regression. And sometimes what we do is we put covariates in first and then the predictor of interest. So we put covariates in the model and then we put the predictor of interest in and see what happens. We see if it's significant, if it has a big effect. In general, I'd recommend these two. We don't talk about this one. This is a good approach. The covariates, then predictor of interest. With assumption checks, luckily Jamovi makes these fairly straightforward. My tutorial should go over that. Reach out if you have questions about checking the assumptions. Again, multi-collinearity is when two or more predictors are very related to each other or are linear combinations of each other. So things that are perfectly related or semi-related can sometimes cause problems in a regression. They need to be pretty correlated for it to happen, like 0.6, like an R value of 0.6 or higher is usually necessary for them to actually start to really cause problems. But that's just a rule of thumb. How we check this is usually checking correlations between variables. And we need to make sure dummy codes are correct. We don't even talk about that in this class because Jamovi does it automatically. When it comes to interactions, as a reminder, it's when the effect of a predictor on the outcome depends on another variable. Here's an example. We used this in class before where you have the tutor, no tutor, group tutor, or private tutor. And the lines are whether you identify as male or female and the GPA. So the interaction here is significant because it's saying the effect of having a group tutor or a private tutor compared to no tutor depends on your gender. If you are male, there is some benefit to going to a group tutor and a private tutor, but not a ton. If you're female, there's quite a bit of benefit. Also, if you're female, the private tutor is by far the best, where for males, group tutor and private tutor are roughly the same. Again, when we put variables in the model, sometimes they may actually interact with each other. And this is another place, like variable selection, that you need to consider theory, you need to consider intuition. Should these variables interact and what would the interaction look like before just throwing stuff in a model? What's nice is Jamovi can do this. You just tell it to do an interaction in the model builder part, and this will take care of it. It'll throw in an interaction for you. This last part of the slides are a challenge for you to go through to see if you can answer any of these questions. It gives you a situation and sees what method might fit this the best. We're not going to go over it here in this recorded lecture, but it's there for you to practice, and feel free to reach out if you have questions about what the answers are for each one. As a reminder, if you have any questions or concerns about part 1 or part 2 of week 10's lecture, please post it to the discussion board. I'll take a look at those and we'll try to cover those in class where we can. Make sure you read the book, see what it says about regression there. But the book overall doesn't go into enough depth. So most of what we're going to use for exams are going to be the stuff that we go over here in the lectures themselves.